All right, well, thank you, and thank all of you. This has been a wonderful conference, and in particular, the organizers. I'd also like to thank my colleagues at University of Chicago and also for some support from IBM, including some sponsorship and some access to certain devices. So I'm going to talk about timescale separations, and that will end up meeting something that we've seen all week. But first, I'll start with some mathematical introduction, but some probably fairly soft mathematical introduction. So I think many of you are familiar with the notion of a quantum channel, which is a completely positive trace preserving map on states, or if you're more in the mathematical area, you might prefer to think of the unital completely positive map on a von Neumann algebra. And you could actually define this between two different algebras or state spaces, but for all of this talk, I will be most of it at least, I will be looking at channels that go from a space to itself. And of course, in the more physical intuition, we would think of this as taking some unitary process on a system and its environment, and then losing the environment, and therefore getting some possibly non-invertible dynamics. So in particular, I want to think about channels that happen in continuous time. And so I would add some parameters so that there's a time interval, and this is going to describe the physical process over this interval. Now, in most of this, we would like to think about divisible channels, not necessarily because they are more physical, but because they're much more tractable to analyze in some of these ways. And here, that would mean that if we take the channel on two consecutive intervals, that is equivalent to taking the channel on the whole. And another property that will sometimes be very useful is that this is truly Markovian, in the sense that the action of the process depends only on some kind of a time-independent environment, and therefore we can think of it as parameterized in terms of just a time difference and not necessarily a full interval. So in general, we'd think of channels in this sense as describing segments of a time evolution. And finally, it's very useful if the time parameterized channel is differentiable in the sense that there is a Lindbladian generator. And again, we would think of this as a composition of a Hamiltonian component, which would actually, if that were all that were there, this would essentially be the Schrodinger equation. But then we can also have some dissipative dynamics, which will lose information to an environment and make this a non-unitary process. And in this case, I've written these very generally so that everything is allowed to be time dependent. I won't always do things that generally, although often we would like to.
Excuse me, can I ask something? I'm confused. Do you require time homogeneity or not? Can you deal also with the cases of having a time-dependent Lindbladian, or do you want to be constrained to the cases where that's not the case? Because I think in your previous definition, we should go one back, right? Do you necessarily have this strong form of what you call Markovianity, or can be more general?
I think Markovian here is actually a misnomer.
Yeah. It would be more semi-group, right?
Okay.
Or stationarity or something like
Stationarity,
that.
yeah, okay, that might
Capture
be
it better, because Markovian has more to do with the concatenation relation that have you above. That
yeah, okay.
Or time homogeneous Markovian.
Yeah,
But
it's
this is
time
very
homogeneity, right? So
This is
station-
very time dependent.
Yeah, but you don't need then to impose time homogeneity, right? So if you think in the language of channels, right, you can imagine that then you have on every step, right, a different generator of Lindblad form, but just different in each time interval. So I'm just wondering whether you do require this strict form or whether you can also do it in general, just imposing divisibility, CP divisibility.
So I would say that's going to vary. And so I'll mention some results that are assume the stationary setting, but then sometimes we can actually get back to just having the divisible setting. And so I would say this is very important. This property is kind of sometimes we'll need it, sometimes we won't.
So we agreed to call that time homogeneous Markov.
Yeah, although I think
Scenario.
yeah, so you could say that this should really be called stationarity. Usually when I see quantum Markov semigroups, they're really talking about this. I really see someone say quantum Markov semigroup when they mean this.
The semi-group.
If we say semigroup from the beginning, it's clear.
Yeah, okay. So yeah, this would have a generator. That generator in full generality is allowed to depend on time. And so the questions that I want to ask now are what happens when we combine different kinds of these systems? And a particular case of that is what happens when we add a perturbation of one kind to something, some original system. And I will say that I actually changed this talk quite a bit after seeing the last few days, because I think that it has connections to all of the main themes at this workshop. And so I want to thank the organizers for putting together something that looks so broad and yet is actually very cohesive and connected. And I'll get into some of the specifics of why as I go through this. But there's a lot of xenodynamics, decay theory, and von Neumann algebra theory that will all come into play in this type of study. So this will have three main parts. And the first thing I want to focus on, which will partially recall some of what we saw on Monday, is dissipative dynamics. And this is where I will start with some more mathematical definitions. So if we take a channel on a von Neumann algebra and a normal semi-finite faithful state on a von Neumann algebra, we can define a GNS Hilbert space and a GNS inner product with respect to that state. And so that will allow us to think of states or operators on that von Neumann algebra in that GNS space. And then we can identify them with GNS vectors, which I will denote with these cats. And there's also the famous Choi-Jamilkowski isomorphism, which says that now we can take the superoperator channel and associate that with an operator on the GNS Hilbert space. So one of the main uses of that in studying decay theory is that we can start to reason about the spectrum associated with a channel or the spectrum of its Choi operator. And so in this case, what we'll mostly think about is when we do have a quantum Markov semigroup, and that quantum Markov semigroup has a fixed point projection. And so this would project to a subspace of states or operators on which this channel will actually act as an identity. And so denoting the fixed point projection E, we have a notion of a spectral gap, which is given by either the norm of the difference of the Choi matrices or the norm going from the GNS Hilbert space to itself. And here is a figure that actually comes from a slightly different context, but I think is very illustrative. This is from a paper involving 3 people who are actually here. It was a Creative Commons license, though, so I think that is implies I can use the figure. And So this is showing the spectrum of sort of a quantum channel, just visualizing some arbitrary version of it. And often what we care about are points that are either whether the spectrum has many points that are on the boundary or that are bounded away from the boundary. And so here they actually have the notion of this delta, which is in this case taken to be smaller than 1. Now, this is not exactly the same notion of a spectral gap that we use, because we're taking this in relation to a fixed point projection, but some of the similar intuition will still hold. And so when this is less than 1, we would think of that channel as actually in some sense causing decay necessarily towards the fixed point. And another thing to note that I think maybe some years ago was fairly worrying in quantum computing is that having this be 1 or having no decay is not a particularly robust property. If we add a small perturbation to a quantum channel, we can easily cause it to have some non-trivial spectral gap and true induced decay. So finally, a little bit more von Neumann algebra theory. This is the Tomita-Takasaki operator for a pair of states rho and omega. And this has some sort of defining relation with the GNS Hilbert space, and that an operator on a GNS vector for one of the states, it will take it to its adjoint or conjugate on the other. And what we would generally do is polar decompose this into modular conjugation and a modular operator. And that modular operator would then be used to construct the modular automorphism group, which conjugates to imaginary powers. Now in type 1 or 2, so for example, in finite dimension, this would actually be a unitary time evolution. And this will often be interpreted as acting like some kind of a Hamiltonian time evolution, in fact. But what do we use all these objects for? Well, one of the first notions that I will recall is that of GNS detailed balance, which is given by commutation with this modular automorphism group, and also self-adjointness of a channel with respect to this inner product. And what does that imply? Well, first, it ensures that there is, in fact, a fixed point subspace and a projection to it. And at least within finite dimension, it would ensure that if we take the infinite limit of time for a quantum Markov semigroup, we would that would be equal to that fixed point projection, which would also now be a conditional expectation, and it would have an associated von Neumann algebra inclusion. So now, okay, this would probably say when it's a semigroup or something, we would say that this would also, in finite dimension, ensure that it has a spectral gap and pretty much eliminate any non-trivial unitary action. So this is one notion of saying that things are purely dissipative. I'll also use some of the modular theory to link back to something that probably is more familiar. This is the relative entropy, and you can actually define it in a modular way, but use also this more familiar tracial definition. This has a data processing inequality, so it's not increasing if you apply a channel to both arguments. And this is an upper bound for trace distance and many resource measures. I don't think I have to say too much to motivate this with this crowd. I think many of you have seen forms of this.
Can I ask you a stupid question? So I know this is a relative modular operator. It's the same thing, right? What you call a modular operator, left multiplication.
Yeah, you can define this with one state, and I guess then it's not relative. But yeah, I'm noting a relative modular operator here. And so now we get to the notion of a modified logarithmic Sobolev inequality. And here I'll state this in terms of relative entropy decay, an exponential relative entropy decay. And so this says that if we apply a semigroup to both arguments, where one is an initial state and the other is a fixed point projection of that state, we will see an exponential decay in time with a uniform constant. And now it was, of course, strengthened to this complete version, CMLSI, or sometimes we call it just CLSI, that allows for an arbitrary tensor extension. So we can put on an auxiliary system. And the main actually motivation for doing this is that it makes the inequality tensor stable. So now if we tensor together things that have this property, their tensor product will have this property as well. And this has been studied by a great many people, and some of them have studied other forms of log Sobolev inequality, which I won't get too much into. But one of the reasons why we like this so much is that it plays very nicely with divisibility. In fact, I would say that this is a divisible notion in the sense that, so we can take this for very small t, and the exponential will become approximately a linear subtraction. And then we can recompose that and actually get an inequality from this that is now allows us to have a time-dependent generator. The condition on that time-dependent generator is that it must still have a consistent fixed point subspace projection. Otherwise, things can get very complicated. But if we take some generators that all have different CLSI constants to the same fixed point, and we compose infinitesimal time evolutions by them, we will really just be averaging or summing up the infinitesimal decays. Now, a little bit more von Neumann algebra stuff and math here. We also will think of things in terms of these CP order inequalities. And so this is actually sort of the channel version of the semi-definite positive order on operators. But the way that I often think about it sort of intuitively is that if phi is greater than or equal to 1 minus epsilon psi, then we can write phi as a convex combination of 1 minus epsilons. Sorry, this should be psi plus another channel. And so with this, we recall the notion of the Pimsner-Popa index, which is the smallest number that we need to multiply the conditional expectation by so that in this ordering, it would dominate the identity. And now some of the recent results on CLSI and decay, Gao and Rouset in 2021 showed that if you have GNS detailed balance in finite dimension, you always have CLSI. So you always have exponential relative entropy decay in this strong tensor stable form with some constant. And then in the recent work with Li Gao and Marius Junge and Haojun Li, we showed some bounds on these constants, in particular that the CMLSI rate is given in terms of the logarithm of the Pimsner-Popa index and the spectral gap. And so this is actually a very nice formula, first because it's reasonably easy to evaluate this, at least in finite dimension. And second, we show that it's saturated, at least in asymptotics for some cases. So for boundness general, this is essentially tight. And there's also a bound in terms of CP order convergence that says if we take a high power or a large time for a semigroup and can show that this is CP order comparable to the fixed point projection, then we actually have a rate bound in terms of the inverse of that time. And so what that's saying is that if we know that the channel eventually gets very close to its fixed point projection, that tells us about the short time dynamics of it, that it must be making at least a little bit of progress in relative entropy decay, even for times being very small. Finally, as sort of a side effect of some of the methods used to prove this, we extended this inequality to general von Neumann algebras. And originally we were using von Neumann algebra techniques to go from the trace symmetric setting to the GNS symmetric setting. But as it turns out, once you're already doing that, we use things like the Hagerup reduction and get to from finite von Neumann algebras to type 3. And so this was talked about a lot by Li Gao on Monday. So I'm not going to go much deeper into this result. But this is kind of saying that in the dissipative regime, we do now have a fairly good and now really filling in picture of decay. And we do see exponential relative entropy decay, and we do see very strong, as I would say, divisible forms of decay in this setting. So on to part 2. What happens is we put the Hamiltonian part back in. So this is leaving the detailed balance setting and now going to somewhat more general form, although we can still study quantum Markov semigroups of this kind. So I'll skip the very technical theorem and go to the slightly less technical corollary. And one thing that may come to mind is that now we have an opportunity for a strong damping regime to appear. And so this is actually a strong damping theorem or corollary. It's saying that we take some contraction semigroup generator that has a fixed point projection and does converge in CP order to its fixed point. And we compose that with a Lindbladian L, which also needs to be a contraction and bounded in this case, but otherwise can be fairly general. And this equation is actually a Zeno type of bound. So this is the original dynamics, and this shown here is actually a form of Zeno dynamics.
Yes, excuse me. The Lindbladian means you are having a Feynman algebra or something. Lindblad means you are working on a Feynman algebra. Or
So Lindblad, what are you saying?
where is it? On which space?
So this is actually fairly general, what space this can be on. However, the fact that this L is bounded is making this a lot more specific. And so I would say this this would hold in infinite dimension, but we kind of know that bounded Lindbladians have these.
What do you mean by Lindbladian? I don't understand.
Yeah, so a generator of a superoperator. So
Yeah, but that would be on a Feynman algebra or
yeah, so I guess the Lindbladian itself would be a superoperator on a von Neumann algebra.
yeah, right. Then where is the other Banach space coming into picture? Which Banach space you are talking about?
So in this case, so in principle, you could think of like this being, because I said Banach space generator, I didn't quite assume that this is a von Neumann algebra. That's what you're saying.
What's the
You are mixing the two, so I don't understand. So E is the same as the acting on that same Feynman algebra, or is on some other Banach space?
So I guess you could actually look at about of this form without assuming that the thing L acts on is a von Neumann algebra, as long as it's a Banach space and it's bounded in some some norm that has the right properties.
Because it's acting on a Banach space. I don't know what it meant by a Lindbladian. So for me, Lindblad means a generator of a quantum Markov semigroup, right? It should generate a CP thing. So at least you need an operator system or something.
Yeah, okay, so this should probably, I mean, this can be a von Neumann algebra. I shouldn't have said Banach space here.
Yeah, please continue.
But then. Okay.
Yeah, so now this is the theorem that I would like to get to, that now we have a Lindbladian with a Hamiltonian part and a dissipative generator. And if we assume that for every density rho, this has a exponential decay to the fixed point. So this would be implied by something like a CMLSI or a similar type of inequality with rate 0, then we could analyze what the decay rate of L actually is. And so the first thing is that if the Hamiltonian represented by conjugation commutes with the fixed point projection of S, then the CLSI constant will basically pass through. And you can see this again using divisibility, taking a Trotter decomposition of L, and that in the Trotter limit, you would see little tiny time slices on which either L or either S or H is acting. And each of the ones that S acts on would induce a sort of infinitesimal time exponential decay. And then you can pass the Hamiltonian through that and end up seeing that they're acting basically independently in this case. So if it does not commute, then we actually see a breakdown of CLSI. And furthermore, if there is a bound here, which actually could be in trace distance or relative entropy, or several other measures, that says that this has an exponential decay rate. The exponential decay rate of L is then upper bounded in terms of the an inverse function in the decay rate of S. And so we see that there's some non-monotonicity in the decay rates and how they depend on each other. And that's coming from the emergence of xenodynamics. So to illustrate that, I'll take a simple example, which is a spin chain. And in the spin chain, this is just 4 qubits. I have constructed a Lindbladian with nearest neighbor interactions between adjacent pairs of qubits, and then applied a polarizing noise to the left end of the spin chain. And so the fixed point projection for this entire spin chain is going to be the completely mixed state, because over time, these interactions will spread the noise down the chain, and we should expect the entire thing to eventually reach mixture. However, we see a couple of things with this. So here are some simulations for varying noise strength parameter and showing the relative entropy over time. The first thing we see, and the state is chosen somewhat specifically to illustrate, is that sometimes the early time decay can be very, very slow. And in this case, all of the purity or coherence in the state is at the right end, while the noise is at the left end. And so what we're seeing here is this flat part is really the time it takes for the noise just to propagate down the chain. So that does break MLSI, although it's a fairly maybe a fairly straightforward phenomenon. Now we do see some decay emerge after finite time, and what's often a little bit stranger here is that you note that the slowest decay is actually both the weakest and the strongest noise. And so that's really coming from this emergence of a Zeno regime. If we fix the time and plot the relative entropy as a function of noise strength, then we see a rebound effect. And in fact, in this example, the rebound effect is extremely pronounced. The strong noise regime is really leaving a lot of information intact in this system. And so why is this happening? Well, if we take the original model, this has interactions between all of the qubits and a noise term with a controllable strength parameter gamma, and we tune gamma up towards infinity. The regime that we reach is actually that of the xenodynamics. And in the xenodynamics, this first qubit is going to be completely mixed pretty much instantly. It's infinitely strong noise, but it will also completely turn off the coupling to the rest of the chain. And so we see here that this qubit is almost immediately lost and mixed, but the rest of the chain is going to remain in a pure state if it starts in one, or at least in the not fully decayed state. And the xenodynamics would actually keep that for an unboundedly long time. So this is a simpler example. It also could be thought of as a spin chain. It's a 2-qubit spin chain. And it has, again, an interaction term and depolarizing noise on the first qubit. This was simulated using a couple different methods with different Trotter step numbers and a version that claims to be able to do this continuously, which all give very similar answers. Again, we see a weak noise regime in which the system remains coherent up to this time scale, a large noise regime in which we actually see a rebound in information preserved, and a strong decay regime in which the strengths of these terms are comparable to each other. And so the fastest decay is actually coming when the noise and the Hamiltonian are somehow on related scales or similar scales. So there's also a way to do this in an experimental analog, which is to look at a version of the generalized Zeno effect, in which instead of having continuous depolarizing noise, there are interruptions by a completely depolarizing channel on the first qubit, interspersing the application of what will eventually be a ZX gate. And what we again see is that now this is plotting distance from the original state. And this is because this has a reasonably nice theoretical bound on it. And again, indeed, we see that the emergence of xenodynamics is going to protect the system and suppress the spread of noise. So yeah, I will also, so I'm going to go very briefly through other things I found. If you discretize the time and choose a minimal time scale, there is a sense in which one can get back a very CLSI-like decay result. And the sort of price for this is that this decay constant isn't uniform in that time scale, which captures the fact that you can't extend this to infinitesimal time. And then the other thing that I would like to emphasize in particular is that I do believe that if you leave the Lindbladian approximation and go to a situation in which you have a Hamiltonian and an environment, this is a theorem from a paper of Daniel and co-authors, and actually three of the authors are here. And this is showing a essentially a Zeno dynamics induced by one Hamiltonian in another. And this actually, I believe, leads to, in the limit, the same sort of result. So this partially is another answer to your question of what about all the regime assumptions that are built into these Woodblottian and Hamiltonian constructions. One should be able to get many of the same things simply comparing Hamiltonians. And in this case, it will have a reversal, which turns out to be very similar to dynamical decoupling. In that if all of the dynamics are modeled as Hamiltonian, then having the system be, in some sense, much stronger than the environment leads to suppression of general environmental interactions. And so those are the key points. And now I will actually stop and take questions.